A total war demands more than soldiers and strategies. It demands imagination, urgency, and a brutal will to experiment without limits. During World War II, all fronts became laboratories where ingenuity ceased to be an option and became survival. Technological innovation accelerated at an unprecedented speed, driven by the need to defeat, resist, or destroy faster than the enemy. The battlefield ceased to be predictable. Bombs that flew with living wings were designed, cannons that required entire trains to fire, dogs trained to detonate tanks, and weapons so strange that their own creators doubted their utility. Nothing was too absurd if it promised an advantage. Ingenuity became dangerous. Science, one more trench. What happens when logic yields to desperation? What type of war is born when rules cease to matter? And how many of those ideas survived the conflict? Total war, the birth of uncontrolled ingenuity. World War II forever transformed the relationship between science and destruction. Between 1939 and 1945, the world witnessed an unprecedented technological acceleration, where the urgency of conflict pushed engineers, scientists, and military designers beyond the conventional limits of armament. This was not simply a war of numbers or strategy. It was a ruthless competition for technological supremacy, where each side bet astronomical resources in the search for that definitive weapon that would tip the balance toward victory. The very concept of military innovation changed radically during these 6 years. What was previously developed slowly in military academies and university laboratories now had to materialize in months or weeks. The constant pressure of active combat turned battlefields into testing laboratories, where barely tested prototypes faced enemy fire directly. This extreme urgency gave rise to developments that challenged not only established military logic, but the very laws of physics and engineering. Germany led this race toward the extraordinary. The Third Reich established an unparalleled military scientific infrastructure, concentrating thousands of engineers in secret complexes like Peenemünde, where the first ballistic missiles in history were born. Under the direction of Albert Speer's Ministry of Armament, specialized units emerged like the Special Weapons Office, which channeled proposals considered too radical for conventional departments. This German obsession with extreme technological solutions intensified as the war turned against them, feeding the Wunderwaffe propaganda, miraculous weapons that would supposedly change the destiny of the Reich. The Nazi ideology of the Wunderwaffe was not mere propaganda. It was a military doctrine that prioritized disruptive innovation over mass production. While the United States built thousands of B-24 bombers and the Soviet Union produced T-34 tanks in industrial quantities, Germany was betting on creating a dozen revolutionary prototypes. This philosophy generated genuine innovations that would influence later decades, but also produced artifacts whose functionality bordered on the absurd. On the other side of the Atlantic, Great Britain responded with its own version of extreme experimentation. Winston Churchill authorized the creation of the Special Operations Executive, an organization that combined traditional espionage with radical technological innovation. SOE laboratories developed everything from explosive pencils to sabotage devices camouflaged as everyday objects. In parallel, the Directorate of Miscellaneous Weapons Development worked on projects that surpassed the limits of the conventional, from amphibious tanks to rockets propelled by giant wheels. The United States established the Office of Strategic Services, precursor to the CIA, which integrated scientists from prestigious universities into classified programs. American laboratories not only worked on the Manhattan Project, they explored everything from psychological chemical weapons to animal control systems for combat missions. American industrial capacity allowed even the most extravagant ideas to receive funding and complete development, reaching in some cases testing phases with unexpectedly destructive results. The Soviet Union, faced with the most massive invasion in history, adopted a pragmatic but equally radical approach. Soviet doctrine prioritized simple and economical solutions that could be implemented quickly at the front. This led to the development of systems that, although primitive in appearance, demonstrated real effectiveness in combat conditions. The Red Army experimented with biological resources, rudimentary remote-controlled devices and tactics that violated all previous military conventions. Japan, geographically isolated and limited in resources, developed a military philosophy that combined samurai tradition with extreme technological innovation. The doctrine of total sacrifice materialized in weapons designed specifically for suicide missions, from manned rocket aircraft to dwarf submarines. These were not desperate improvisations. They were planned, tested, and operationally deployed developments reflecting a military mentality that prioritized psychological impact and destructive efficiency over operator survival. This global convergence toward radical military experimentation produced arsenals that challenged traditional classification. Weapons emerged that combined aeronautical engineering principles with animal control systems, devices that fused rocket propulsion with wooden structures, and vehicles that redefined basic concepts like mobility, armor, and firepower. Many of these creations were effective in specific contexts. Others failed spectacularly. All represent tangible testimonies of an era where the line between innovation and desperation became indistinguishable. The time factor was determinant in this evolution. Unlike peacetime periods where new military technologies developed gradually over decades, World War II compressed complete cycles of research, development, testing, and deployment into periods that rarely exceeded 2 years. This acceleration produced genuine advances that laid foundations for later developments, but also generated an extraordinary quantity of projects that, although functional, proved impracticable for real war. Krummlauf, the shot that never exposes the soldier. The urban combats of Stalingrad had taught a mortal lesson. The first soldier to turn a corner rarely lived to tell the experience. This brutal reality forced German engineers to develop a solution that defied the fundamental laws of ballistics, a cannon capable of firing at an angle, allowing the shooter to remain under cover. Thus was born the Krummlauf, an accessory designed to modify the Sturmgewehr 44 assault rifle and allow firing around obstacles without direct exposure. The origin of this weapon is found in reports from the Eastern Front, where house-to-house warfare revealed clear patterns. Most casualties occurred at the moment of advancing through narrow corridors or turning corners in ruins. Internal Wehrmacht statistics confirmed that assault units suffered disproportionate losses in these scenarios. To respond to this recurring threat, the High Command authorized the urgent development of a system that would reduce risk in urban environments. The solution had to be portable, low cost, and compatible with existing weapons. The Krupp contractor was charged with materializing the concept. Variants were designed with curvatures of 30, 45, 60, and up to 90 degrees, each destined for different uses. The higher angle versions were intended to be mounted on armored vehicles, especially in blind spots where it was impossible to aim directly. The 30-degree version was the only one produced in significant quantity, as it offered an acceptable balance between mechanical resistance, firing precision, and useful life expectancy of the barrel. The Krummlauf was not simply a curved tube. The design incorporated a periscopic optical system that allowed the operator to aim without sticking his head out. This sight was composed of a set of mirrors mounted at angles, protected by a metallic casing. To avoid ballistic distortion, a special rifling was developed that guided the projectile in its curved trajectory. However, this adaptation introduced enormous tensions on the structure of the barrel and the projectile itself. Laboratory tests revealed that bullets suffered progressive deformations, especially when exceeding 250 shots per unit. German engineers faced multiple technical challenges. One of the main ones was the internal fragmentation of the projectile. In many cases, the bullet did not resist the forced turn inside the barrel and broke apart, generating a chaotic firing pattern similar to that of a shotgun. This drastically reduced penetration and affected shooter safety. Despite attempts to reinforce the projectile, the phenomenon persisted due to the physical laws involved in such a forced curve. Troop training required visual re-education. The periscopes inverted spatial orientation and altered depth perception. User manuals included specific exercises to recalibrate aim and understand how curvature affected trajectory. Selected units performed practices with moving targets and objectives protected by artificial corners to simulate real urban combat. The urban combats of Stalingrad had taught a mortal lesson. The first soldier to turn a corner rarely lived to tell the experience. This brutal reality forced German engineers to develop a solution that defied the fundamental laws of ballistics, a cannon capable of firing at an angle, allowing the shooter to remain under cover. Thus was born the Krummlauf, an accessory designed to modify the Sturmgewehr 44 assault rifle and allow firing around obstacles without direct exposure. The origin of this weapon is found in reports from the Eastern Front, where house-to-house warfare revealed clear patterns. Most casualties occurred at the moment of advancing through narrow corridors or turning corners in ruins. Internal Wehrmacht statistics confirmed that assault units suffered disproportionate losses in these scenarios. To respond to this recurring threat, the High Command authorized the urgent development of a system that would reduce risk in urban environments. The solution had to be portable, low cost, and compatible with existing weapons. The Krupp contractor was charged with materializing the concept. Variants were designed with curvatures of 30, 45, 60, and up to 90 degrees, each destined for different uses. The higher-angle versions were intended to be mounted on armored vehicles, especially in blind spots where it was impossible to aim directly. The 30-degree version was the only one produced in significant quantity, as it offered an acceptable balance between mechanical resistance, firing precision, and useful life expectancy of the barrel. The Krummlauf was not simply a curved tube. The design incorporated a periscopic optical system that allowed the operator to aim without sticking his head out. This sight was composed of a set of mirrors mounted at angles, protected by a metallic casing. To avoid ballistic distortion, a special rifling was developed that guided the projectile in its curved trajectory. However, this adaptation introduced enormous tensions on the structure of the barrel and the projectile itself. Laboratory tests revealed that bullets suffered progressive deformations, especially when exceeding 250 shots per unit. German engineers faced multiple technical challenges. One of the main ones was the internal fragmentation of the projectile. In many cases, the bullet did not resist the forced turn inside the barrel and broke apart, generating a chaotic firing pattern similar to that of a shotgun. This drastically reduced penetration and affected shooter safety. Despite attempts to reinforce the projectile, the phenomenon persisted due to the physical laws involved in such a forced curve. Troop training required visual re-education. The periscopes inverted spatial orientation and altered depth perception. User manuals included specific exercises to recalibrate aim and understand how curvature affected trajectory. Selected units performed practices with moving targets and objectives protected by artificial corners to simulate real urban combat. Yokosuka MX-67 Ohka, the high-speed kamikaze. When American air defenses became impenetrable for conventional Japanese aircraft, the Yokosuka naval arsenal conceived a response that completely eliminated the concept of return. A manned flying bomb designed to overcome any interceptor through pure speed. Thus was born the MX-Y-7 Ohka, whose very conception represented a radical change in the armament thinking of its era. The logic behind the Ohka was direct and brutally pragmatic. American fighters were systematically shooting down Japanese bombers before they could get close enough to their objectives. Conventional bombs failed against the reinforced armor of battleships and aircraft carriers. In this scenario, the only way to ensure direct impact was to integrate the weapon and the pilot into a single system. The Ohka design completely eliminated any superfluous element, without landing gear, without instrumentation for return, without redundant navigation systems. Everything was subordinated to a single objective, to carry a massive explosive charge at maximum speed against a naval target. The fuselage was constructed with a combination of duralumin and laminated wood, responding to the double requirement of lightness and material availability. This configuration reduced weight without completely compromising structural integrity. The central explosive charge, of 1,200 kilograms of amatol, was housed in the front part of the fuselage, optimized to detonate with prior penetration. At that terminal velocity, even battleships with reinforced armor were vulnerable to direct impacts. Propulsion was achieved through 3 Type 4 solid fuel rockets developed by Kayaba Kogyo, each with a combustion duration of 10 seconds. Together, they provided a thrust of 800 kilograms, sufficient to take the Ohka from an initial gliding speed to more than 930 kilometers per hour in its terminal phase. This brutal acceleration made it practically impossible to intercept by American escort fighters in the critical seconds prior to impact. However, the design implied a severe structural limitation. The Ohka needed to be transported to the launch point by a Mitsubishi G4M2E Betty bomber. This aircraft had to approach less than 30 kilometers from the naval objective before releasing the projectile. For that phase, the Ohka descended gliding to an optimal operational altitude, at which moment the rockets were activated. This absolute dependence on the mother bomber became the fundamental operational vulnerability of the system. Japanese bombers, large and slow, were priority targets for American fighters. Many were shot down before even reaching the release point. This situation compromised the complete system. The loss of a single bomber meant the destruction of the Ohka and its pilot before even beginning the mission. Despite air escorts composed of Mitsubishi A-6M0 fighters, Allied air supremacy in the Western Pacific made it extremely difficult to successfully complete the deployment cycle. The training of Ohka pilots was specific and accelerated. Many of them were young men without real combat experience. Their preparation centered on gliding control, spatial orientation at high speed, and identification of naval targets from medium altitudes. Motorless gliders were used as part of initial instruction. The Ohka controls were deliberately simplified, reduced to a minimum necessary to adjust elevation and direction in the last seconds. No escape mechanism existed. Once the descent was initiated, the pilot became part of the weapon. Operational deployment began in the Battle of Okinawa in April 1945. The formations consisted of waves of bombers, each carrying an Ohka in its lower part. In total, Japan produced more than 850 units, although only 74 were launched in real combat. Most were destroyed before reaching activation distance. In some cases, the enemy managed to detect the approach and maneuver out of the attack angle before impact. Nevertheless, successful impacts demonstrated considerable destructive power. The USS Manat El Abel, an American destroyer, was sunk after a direct Ohka impact, marking the first confirmed victim of the system. Other ships, although not sunk, suffered severe structural damage. The explosive penetrated deck and produced massive fires in internal compartments. Technical naval reports from the U.S. Navy noted that the Ohka's impact speed exceeded normal reaction times of short-range anti-aircraft systems, making it especially difficult to neutralize in its terminal phase. Despite its limitations, improved versions were developed, such as Model 22, which substituted the rockets for a Tokuro-2 jet engine, significantly expanding operational range. This redesign required modifications in the fuselage structure, increasing fuel capacity and reinforcing key sections. However, it was not implemented massively before Japanese surrender. Launches from I-400 class submarines were also studied, which would have allowed stealthy approaches without bomber dependence, although these options remained in testing phases. The manufacture of the Ohka was delegated to multiple factories in Yokosuka, Kasumigara, and USA. Given the shortage of qualified manpower toward the end of the war, university students and minimally trained civilian personnel were employed. Assembly lines were organized by modules, which allowed rapid assembly with a reasonable degree of precision, although quality control suffered in secondary components not related to propulsion or guidance system. From a technical point of view, the Ohka is considered a conceptual precursor of modern guided missiles. By eliminating concern for vehicle recovery or operator survival, designers could focus all resources on maximizing destructive efficiency. This approach allowed achieving levels of terminal velocity and precision impossible to achieve with conventional systems of the era. The concept of explosive charge integrated with autonomous propulsion would influence later generations of armament air-to-surface, including tactical missiles like the AGM-65 Maverick or the French AS-20. The Allies took note of the design and conducted detailed analyses after capturing intact units. Tests revealed that under ideal conditions, the Ohka had a significantly superior impact probability than any other contemporary Japanese system. However, its logistical dependence, the vulnerability of the mother bomber, and the fact that it could not be reoriented after launch limited its strategic effectiveness. A terrestrial variant of the Ohka was also studied for possible defensive attacks on Japanese territory. This consisted of a launch ramp from camouflaged bunkers using delayed ignition rocket motors to reach nearby naval targets. Although its use was not materialized, technical documents reveal that complete prototypes were built, capable of launching from tunnels or hidden platforms. With the advance of the Manhattan Project and the appearance of nuclear armament, the Ohka quickly became obsolete as a strategic system. However, its legacy remained in studies of suicidal, guided, and high-speed weapon design. In purely technical terms, it represented an extreme solution to a concrete operational problem: how to penetrate a naval defense with limited means, without air superiority nor industrial resources comparable to those of the United States. The MX-7 Ohka was not improvised. It was the result of a formal, structured, and documented program where engineering, military doctrine, and extreme strategic conditions converged. Its later study allows understanding how certain total war contexts permit the development of radical systems that, although limited, manage to achieve operational results when used under favorable conditions. The mechanical simplicity of the Ohka contrasted with the tactical complexity it required to be effective, a lesson that would persist in guided weapons doctrines for decades. Gustav, the largest railway gun in history. The Schwerer Gustav was not simply a large cannon, it was the extreme symbol of a military logic that took the concepts of firepower, advanced metallurgy, and operational logistics to the limit. With a total weight of 1,350 tons, projectiles heavier than a family automobile, and a length of almost 47 meters, this railway gun represented the apex of heavy artillery in the history of modern warfare. In 1934, the German High Command commissioned the Krupp Company a design that, on paper, seemed unrealizable. A weapon capable of destroying reinforced concrete fortifications 7 meters thick, or penetrating steel armor 1 meter thick, while maintaining the peace out of reach of enemy artillery. This request was based on studies of French defenses of the Maginot Line, although the weapon was not completed in time to be used against them. The result was the Gustav, whose design implied a total re-engineering of the concept of mobile artillery. The cannon had a tube of 32.5 meters in length with a caliber of 800 millimeters. Its structure required a double parallel railway track to distribute its enormous mass. 80 special wheels mounted on 5-axle bogies supported the load on 2 articulated chassis. This complexity was necessary to support recoil, dynamic balance during firing, and stability on variable terrain. The Gustav's ammunition was as extraordinary as its size. 2 main types of projectiles were designed. One explosive of 4,800 kilograms with a maximum range of 47 kilometers and another armor-piercing of 7,100 kilograms, which could impact targets at 38 kilometers with a force capable of penetrating underground bunkers. Each projectile required loading with a special crane and was accompanied by separate propelling charges inserted manually by trained operators. Only the loading operation could take up to 45 minutes. The construction of the Gustav was an unprecedented metallurgical challenge. Krupp developed special steels with progressive thermal treatments to withstand the internal pressures of firing. The forging of the main tube took several months, and its assembly required customized industrial installations. The cannon was tested for the first time in Rügenwalde, where controlled shots were conducted to verify structural integrity, precision, and recoil behavior. These trials revealed that the cannon needed constant adjustments in its railway suspension system due to micro-deformations caused by the shots. The operational deployment of the Gustav demanded an unprecedented mobilization. Between 4,000 and 5,000 soldiers were required, more than 20 special wagons, hauling locomotives, assembly cranes, and qualified technical personnel. The construction of the parallel track took from 3 to 6 weeks, depending on terrain. In addition, defensive positions, camouflage, command centers, and heavy anti-aircraft batteries, such as the Flak 88 and Flak 128, had to be established to protect the position against Allied attacks. The only operational use of the Gustav occurred during the siege of Sevastopol on the Crimean Peninsula in June 1942. The weapon was transported by train through Poland and Ukraine to the railway port of Bakhchisaraj, where it was mounted on a special track built for the purpose. From there, between June 5th and 17th, the Gustav fired 58 projectiles, destroying multiple heavily fortified objectives, including the White Cliff Underground Magazine and Fort Stalin Fortress, which resisted conventional attacks. Craters of up to 30 meters in diameter and structural damage of great depth were recorded, confirming that the weapon was technically capable of fulfilling its original function. However, practical problems became evident. The rate of fire was extremely slow. a single shot every 30 to 45 minutes due to reloading time, alignment and pressure verification. The cannon required tube replacement every 50 shots due to internal wear. Added to this was the system's vulnerability to Allied aviation. Any successful air attack could render the entire operation useless in minutes, despite mounted defenses. A second unit was built, called Dora, which was deployed near Stalingrad but withdrawn before being used. There are no confirmed records of operational shots from Dora. A third model, known as Schwerer Gustav, with reduced caliber to 520 mm and projected to fire experimental long-range missiles, was destroyed in its initial phase when the Allies bombed Krupp installations in Essen. The idea of using giant cannons was not new. During World War I, Germany had already built the Big Bertha and the Paris gun, but the Gustav exceeded by an abysmal margin everything that had been attempted before. Its scale made it incompatible with the mobile warfare that was imposed in the second half of the conflict. Increasingly, heavy artillery was replaced by tactical aviation, rockets like the V-2, and mobile multiple launch systems. German High Command reports after Gustav's use recognized that, although technically impressive, the system had consumed disproportionate resources compared to its strategic effectiveness. Ammunition was expensive, transport slow and predictable, and use was limited to static objectives, rarely present on mobile fronts. A single successful bombing could have destroyed the Gustav, nullifying months of preparation. In 1945, as the Soviet front approached German territory, the Gustav was partially dismantled and subsequently sabotaged by its own operators near Auerbach in Bavaria to prevent its capture. American forces found fragments of the weapon, including sections of the tube, wheels, and partial technical documentation. Part of these remains were sent for analysis to Aberdeen Proving Ground, while others were lost. At a technical level, the Gustav was impeccable, precise, powerful, and structurally solid, but its design responded to a type of static and planned warfare that no longer existed in 1942. Modern warfare demanded mobility, adaptability, and rapid deployment. The Gustav could not move with agility, could not fire while moving, and needed weeks of logistical preparation. It was a solution from the past implemented in a future conflict. However, its construction was not useless from the point of view of armament development. Many of the advances in metallurgy, pressure control, composite materials, and reinforced railway structures used for the Gustav were reused in later industrial systems, both civilian and military. Assembly techniques, calibration of large tubes, and large-scale recoil handling influenced the development of Soviet and American space launches in later decades. In its essence, the Gustav was a colossal work of engineering. It had no comparison in terms of size or power, and its very existence demanded an extremely sophisticated industrial and logistical organization. It was not a conventional weapon. It was a piece of artillery that demanded its own army to operate. The Gustav was not mobile, was not versatile, and was not mass reproducible, but for 2 weeks in Sevastopol it was the most powerful cannon in the world. Bomb dogs, the horror of the Eastern Front. While German panzers advanced without effective opposition across the vast Soviet steppes in 1941, the Red Army faced a critical limitation: the lack of anti-tank weapons capable of stopping modern armored vehicles like the Panzer IV, the Tiger I, or the Stug III. This structural shortage led to the implementation of non-conventional solutions. Among them, one of the most radical was the use of explosive dogs as living anti-armor units. The project was not improvised. It was the result of systematic research initiated several years before the conflict. In 1935, the Military Canine Service Directorate, UVVK, began experimenting with the use of dogs in offensive military applications. Soviet doctrines anticipated mechanized conflicts with technologically superior enemies, especially in scenarios where Soviet forces could find themselves outnumbered or outgunned. The USSR already used dogs in messaging, tracking, and rescue functions, but converting these animals into guided weapons was a step beyond. The central methodology was based on operant conditioning. Dogs were trained, mainly German shepherds and large crosses, to associate armored vehicles with food. For weeks, the animals were fed exclusively under static Soviet tanks. Then engine noise and slow movement were introduced. The progression reached real vehicles in motion. In theory, this generated an automatic response. Upon hearing or seeing a tank, the dog instinctively headed under it in search of food. The standard explosive charge consisted of 10 to 12 kilograms of TNT or RDX, installed in a reinforced canvas harness. This harness was designed to distribute weight in a balanced manner and allow complete mobility. A vertical lever protruded over the animal's back, activating the detonator by contact when the dog entered under the vehicle's chassis. The system did not use timers or remote control in its original version. The explosion was produced by direct physical contact. Each combat unit with bomb dogs operated as a specialized platoon composed of 27 dogs divided into squads of 9, each with their handlers. These soldiers received specific training in canine ethology, tactical deployment signals, and evacuation protocols in case of error. Transport to the front was carried out in GAZAA trucks adapted with ventilated compartments. The animals were unloaded at short distance from German lines and released upon receiving visual or auditory signal. The first significant deployment took place in autumn 1941 during defensive operations prior to the Battle of Stalingrad. Operational reports from the 62nd Army indicate the destruction of 3 German vehicles during a synchronized attack. However, critical problems immediately arose. Many dogs, trained with Soviet tanks, did not adequately differentiate enemy and friendly armored vehicles. On more than one occasion, the animals returned toward Soviet trenches, activating the charge in Allied positions and causing significant casualties. In the Caucasus campaign, a unit from the Transcaucasian Front suffered total failure. Under intense artillery fire, the dogs became disoriented, ran in multiple directions, and caused uncontrolled explosions. Casualties included both Soviet personnel and their own animals. These events confirmed one of the structural limitations of the system, the impossibility of controlling animal behavior under real combat conditions. The German High Command did not take long to react. Specific countermeasures were implemented. Immediate execution of any dog seen in combat zones was ordered, xenophobic patrols were established, and tactical bulletins were issued warning about the possible use of animals as mobile mines. However, distinguishing between civilian and trained animals was difficult in rural areas of the Eastern Front, reducing the effectiveness of these measures. Despite initial failures, the program continued. Technical modifications were introduced to improve reliability. An updated version of the harness included automatic charge release if the dog did not reach a target in estimated time. Another variant incorporated remote detonation via cable or radio frequency, although this technology was limited by interference and device fragility in real combat. To improve target identification, dogs were trained using captured German vehicles, thus avoiding confusion with Soviet units. The largest documented deployment of bomb dogs occurred during the Battle of Kursk in 1943. More than 300 dogs were used in massive attacks against German armored units of Army Group Center. Results were mixed. While 56 tanks were damaged or destroyed according to Soviet figures, many animals died before reaching their targets or detonated out of range. Even so, the presence of explosive dogs on the field generated a psychological deterrent effect among some German units. The program did not disappear after the end of the war. It was reabsorbed by defense-in-depth doctrines during the Cold War. The idea of denying passage to enemy armored vehicles in predictable advance zones through the use of animals trained as mobile mines was maintained in Warsaw Pact technical manuals. Soviet documents declassified in the 90s reveal that these systems were retrained to act against NATO armored columns in regions like Poland, Romania, and Western Ukraine. During the Soviet occupation of Afghanistan, unconfirmed reports suggest that deployment tests were conducted in urban zones, especially for surveillance and access denial to tunnels used by insurgents. There is no public evidence that they were used operationally in combat, but interest persisted. The last official document related to bomb dogs appears dated 1996 as part of a Russian contingency plan for possible conflicts in Chechnya. In terms of effectiveness, bomb dogs represented a high-risk weapon with variable performance. Their success depended on unpredictable factors such as weather, visibility, animal mental state, and evolving tactical situation. Unlike static mines or portable anti-tank weapons like the PTRD-41, the dog was an unreliable semi-autonomous platform, but its production cost was low, required little advanced technology, and its training could be completed in a few weeks, making it viable for an army with limited resources. The persistence of the program for more than 6 decades demonstrates that, in military terms, the concept was not discarded. It was considered a useful tool for specific tasks, area denial, installation defense, or selective sabotage. In addition, its deployment generated tactical uncertainty, forcing the enemy to dedicate time, resources, and attention to a threat difficult to predict. In technical analysis, bomb dogs must be understood as a primitive platform of unmanned guided weapon, in certain way precursor to modern technologies like suicide drones, with the crucial difference that the vector was biological. The principle of directed attack through self-induced trajectory based on external training was later adapted to the electronic field. In many ways, these systems anticipated problems that missile developers would later face: target identification, environmental interference, and reliability under extreme conditions. Unlike more complex concepts like the Kugelpanzer or the bat bomb, bomb dogs did not need sophisticated supply chains, nor assembly lines, nor industrial resources. Their deployment was logistically simple and could adapt to changing fronts. This explains their longevity in low-cost military doctrines with high potential impact. Although they were never a decisive weapon, their implementation on hundreds of occasions in open fronts, trenches, towns, and fortified areas makes them one of the most unusual and technically concrete tools within the tactical repertoire of the 20th century. They represented a functional, although limited, solution to a real operational need. Bat bomb, bats with napalm. The letter that changed the course of biological warfare arrived to Franklin Roosevelt from an unexpected place: Lytle S. Adams' dental office in Pennsylvania. After observing bats in Carlsbad caves, Adams proposed an idea so extravagant that the president considered it crazy enough to work: converting flying mammals into vectors of incendiary bombs against Japanese cities of wood and paper. Roosevelt referred the proposal to the War Department, initiating Project X-ray under supervision of Dr. Louis Fieser from Harvard Chemical Laboratory. Fieser's previous experience with napalm made him the ideal candidate to solve the technical challenges of miniaturizing incendiary weapons to scales transportable by bats. Species selection centered on Tadarida brasiliensis mexicana, free-tailed bats abundant in the American Southwest. These animals presented ideal characteristics: significant proportional load capacity, predictable shelter behavior in structures, and resistance to altitude and pressure variations during air transport. Individual incendiary bombs weighed 17 grams, containing concentrated napalm sufficient to initiate fires in combustible materials. Chemical timers provided delays of 20 to 30 minutes, allowing bats to find shelter in structures before ignition. Attachment systems employed miniaturized clips and surgical collars that did not interfere with natural mobility. Specialized cylindrical containers maintained up to 1,040 bats in induced hibernation through controlled refrigeration. This approach took advantage of natural physiological responses to reduced temperatures, keeping them inactive during bombing flights. Parachute systems controlled descent speed for gradual dispersion in patterns that maximized target area coverage. Tests at Muroc, California, included behavioral evaluation after artificial hibernation, analysis of aerial dispersion patterns, and timer verification under variable conditions. Experiments confirmed that bats followed natural shelter instincts, seeking dark spaces typical of attics and basements where fires could spread rapidly. In May 1943, an accidental escape at Carlsbad Army Airfield inadvertently validated destructive effectiveness. Several bats equipped with incendiary devices took shelter in base hangars, initiating uncontrolled fires that destroyed maintenance installations. This incident, documented as unintentional verification, reinforced confidence in the technical viability of the concept. Subsequent controlled tests used mock-ups of Japanese cities that reproduced traditional construction methods. Results confirmed that a B-24 bomber loaded with containers could initiate more than 3,500 simultaneous fires distributed across an extensive urban area, surpassing any conventional incendiary attack. However, maintaining massive bat populations required specialized installations, trained personnel, and feeding systems that demanded significant resources. Coordination with bombing operations presented complications related to synchronization, navigation, and release procedures, that required extensive aircraft modifications. The time factor proved critical. While Project X-ray progressed, the Manhattan Project advanced toward nuclear production that promised destructive capabilities superior to any conventional system. In August 1944, General Leslie Groves requested absolute priority for resources, resulting in official cancellation of the BAT program. The decision reflected strategic calculations that prioritized nuclear concentration over experimental dispersion. Analysts concluded that, although technically viable, the system would require development periods that exceeded operational schedules to conclude the Pacific War. Files remained classified until 1960, when partial declassification revealed the complete extent of the program. Surviving BATs were released in natural reserves where they reintegrated without prolonged adverse effects. The BAT bomb confirmed that apparently absurd concepts can demonstrate technical viability when adequate resources and rigorous scientific methodology are applied. Its cancellation did not reflect technical failure but strategic evolution toward nuclear capabilities that made non-conventional methods unnecessary, regardless of their demonstrated effectiveness in controlled tests. Great Panjandrum, the British rolling ruin. Few weapons in military history have combined extreme technical ambition with such spectacularly catastrophic results as the Great Panjandrum. This rocket-propelled explosive wheel represented the culmination of British experimentation during preparation for Normandy, a device that promised to revolutionize amphibious warfare but ended up being more dangerous for its operators than for the enemy. The Directorate of Miscellaneous Weapons Development conceived the Panjandrum as a radical solution for the coastal defenses of the Atlantic Wall. Planners recognized that German concrete walls and anti-tank obstacles would require massive explosive charges placed with precision, a task that exceeded the capabilities of naval artillery or conventional aerial bombardment. The configuration consisted of two giant wheels of plywood 3 meters in diameter, connected by a central axle that housed 1,800 kilograms of high-power explosives. Cordite RP, 3 rockets installed radially around the perimeter would provide directional propulsion, theoretically propelling the device across the beach toward target fortifications. The operational concept assumed launch from vessels in shallow waters, followed by self-propelled movement through synchronized rocket activation. Without remote control systems or active direction, trajectory depended completely on precise synchronization and uniform wheel resistance on variable surfaces. This dependence on ideal conditions immediately became the fundamental weakness of the system. Tests began in September 1943 at Westward Ho, Devon, a beach selected for topographical similarity to Normandy, but whose non-classified nature allowed unauthorized observation by civilians and even filming by Pathy News. The first trial revealed catastrophic problems. Asynchronous rocket ignition caused uncontrolled rotation, severe lateral inclination, and total loss of direction. The Panjandrum spun violently, moved off the planned course, and stopped when multiple rockets detached due to excessive centrifugal forces. Correction attempts included a third central stabilizing wheel and guide cables connected to coastal controls. These modifications introduced additional complications without resolving fundamental problems. The third wheel interfered with ability to traverse obstacles while cables tangled with rotating rockets and broke during the first phases of movement. Rocket detachment during operation created extreme dangers for observers and technical personnel. Released rockets flew unpredictably with unburned propellant impacting observation positions and forcing temporary suspensions while safety protocols were revised. The most documented demonstration occurred before senior officers and Ministry of Supply representatives, designed to show viability before approval for production. The Panjandrum traveled barely 40 meters before experiencing catastrophic failure. Multiple rockets detached simultaneously, causing total loss of propulsion and partial detonation of explosives due to damage to safety systems. Official observers concluded that the device presented unacceptable risks for Allied forces, including premature detonation, unpredictable trajectory toward own troops, and dangerous fragmentation in areas densely occupied by military personnel. Final evaluation determined that no feasible modification could resolve fundamental limitations of stability and control. The program was officially cancelled in 1944, freeing resources for projects with greater probability of effectively contributing to Normandy operations. No Panjandrum was deployed during D-Day. Prototypes were dismantled with recoverable materials redirected toward conventional systems. Explosive components were transferred to engineer units for standard demolition, while rocket systems were analyzed for applications in missile projects that incorporated active controls to overcome evidenced limitations. The Great Panjandrum perfectly illustrates how technical ambition without adequate consideration of fundamental physical principles can produce systems that, although conceptually innovative, fail spectacularly in practical application. Its development demonstrates both British willingness to explore radical solutions during crisis and the critical importance of exhaustive testing to identify systemic problems before committing resources to operational production. Kugelpanzer, the rolling tank. In the basements of the Kubinka Tank Museum rests one of the deepest mysteries of World War II, an armored vehicle of spherical configuration whose purpose, specific origin, and operational circumstances defy decades of specialized research. The only known Kugelpanzer represents the most extreme example of German experimentation in vehicular design, an artifact that seems more appropriate for science fiction than for historical battlefields. Soviet troops discovered this enigma during the occupation of Manchuria in August 1945. Although exact circumstances remain undocumented. Circumstantial evidence suggests discovery in Japanese installations, possibly as a result of Axis technological transfers that included advanced torpedoes, rocket engines, and other German developments transported by Class 9-D submarines. Dimensions confirm design for individual operation: 1.5 meters in length, 1.2 meters in height, 1 meter in width. Structural configuration is based on two completely enclosed metallic wheels forming the sides, connected by a central cylindrical compartment that contains the operator's cabin. A rear stabilizing roller prevents overturning during irregular movement. Armor protection is deliberately light, between 5 and 8 millimeters thick, sufficient only against fragments or small arms fire at moderate distances. This limitation clearly indicates that the vehicle avoided direct combat, suggesting roles that emphasized stealth, reconnaissance, or specialized support rather than frontal engagement capability. Access requires adopting an almost fetal position within the extremely confined space, severely limiting operational duration due to physical fatigue and claustrophobia. This configuration indicates intended use for brief missions or specialized applications that justified extreme habitability limitations. Vision is provided through a front slot protected by sliding cover, but without advanced optical systems, telescopic sights, or aiming equipment typical of military vehicles. This absence suggests dependence on direct observation, limiting effectiveness in reduced visibility conditions. No identifiable mounting points for armament exist, although speculations suggest possible space for light machine gun coaxial with the vision slot. However, absence of physical evidence of weapons systems, ammunition, or control mechanisms reinforces conclusions that it was not designed for direct combat. The original propulsion system was removed or never complete during capture, complicating analysis of mobility capabilities. Technical evaluations suggest that a small motorcycle engine would have provided adequate power, with differential transmission controlling lateral wheels for directional maneuvers. Absence of conventional suspension indicates dependence on large wheels for impact absorption. Manufacturing marks confirm German origin associated with Krupp, but no records exist in declassified archives documenting specifications, production numbers, or operational assignments. This absence suggests extreme classification or development under special authority that avoided normal administrative channels. The most plausible theory proposes employment as reconnaissance vehicle for stealthy infiltration, taking advantage of its unusual visual profile that would confuse identification at distance. The spherical shape would provide effective camouflage when immobile, especially in terrain with dense vegetation where it could be confused with natural formations. Alternative theories suggest use as liaison vehicle for communications between isolated positions, taking advantage of compact size for mobility in tunnels, trenches, or urban areas where conventional vehicles could not operate. This application would explain light armor and absence of armament depending on stealth rather than protection. A third hypothesis proposes specialized defensive function for critical installations like airfields or depots, where perimeter patrol would provide continuous surveillance without dedicated personnel. Compact design would allow operation in confined spaces typical of underground installations or bunkers. Presence in Manchuria confirms transfer from Germany as part of technological exchanges that included multiple prototypes transported by German submarines. The fact that only one example has been discovered suggests it never progressed beyond experimental phase or that production was extremely limited. Absence of similar vehicles in European theaters indicates that the concept was not operationally adopted by German forces, possibly due to practical limitations manifested during initial tests. Contemporary analyses have been limited by access restrictions and preservation policies that prevent disassembly for detailed internal inspection. The Kugelpanzer remains as tangible testimony of radical German experimentation, when operational pressure and Wunderwaffe ideology drove exploration of concepts that challenged established principles of vehicular design. Its existence confirms German willingness to investigate extremely non-conventional configurations, even when they diverged dramatically from traditional military paradigms. Its preservation in Kubinka ensures that future generations can study physical evidence of one of the most unusual experiments in armored vehicle development, providing perspectives on the limits of technical innovation under total war and the willingness of military organizations to explore radical solutions when conventional methods seem inadequate for specific operational challenges.